Hello, my friends, and welcome back to the You Can Do TV channel. A country with almost no fresh water built a system that exports water technology to the rest of the world. Wastewater recycling at 85%, the highest rate on Earth. Desalinated seawater pumped nearly 900 meters up to Jerusalem. 12,000 kilometers of pipeline linking the entire network. Every component had to be built, connected, buried, and kept running. What follows shows every step of how 60% of Israel is desert, with vast stretches of arid land and very limited natural freshwater. Turning a dry landscape into a reliable water supply system requires far more than conservation. It depends on infrastructure built to manufacture, transport, and deliver water across the country, and that infrastructure starts with pipe. Demand for water has never been more critical. Much of the existing water infrastructure was built in the mid-20th century and was designed to last 75 to 100 years. But at the current pace, experts estimate it could take 200 years to replace the aging network. To bridge that gap, modern engineered steel pipelines are being deployed. Steel has carried drinking water for more than 150 years, while advanced coatings and lining systems help extend service life and improve long-term reliability. Steel carries water under pressure. Concrete carries water and the weight of everything above it. And for large buried transmission lines, reinforced concrete pipe handles both. Four types serve the water industry. C300 reinforced concrete cylinder pipe starts with a welded steel cylinder and joint rings at both ends. Reinforcement cages are positioned around the cylinder, inner and outer forms encase everything, and concrete fills the space. C300 handles deep cover installations and microtunneling. C301 prestressed concrete cylinder pipe lines or embeds the steel cylinder in concrete. Once cured, prestressing wire is wrapped under controlled tension from end to end while cement slurry is applied. A mortar coating finishes the exterior. Pressed pipe is typically more cost-effective than C300 for water and wastewater transmission. C302 uses no steel cylinder at all. Two concentric reinforcement cages carry the structural load, with concrete filling between inner and outer forms for lower pressure applications. C303 bar wrap pipe wraps mild steel bar around a lined cylinder at uniform spacing with cement slurry applied simultaneously, then receives a mortar coating. C303 is lighter, manufactured in longer lay lengths, and reduces the number of joints needed during installation. All four combine the tensile strength of steel with the compressive strength of concrete and mortar. Before any pipe section enters a system, every joint has to be cut to exact geometry. A portable CNC pipe cutting machine handles steel up to 500 millimeters in diameter with 120 millimeter wall thickness. The machine rides a chain track around the pipe circumference, cutting K bevels and X bevels under computer control. A dry run verifies the path before the torch fires. The finished bevel surface comes out clean enough for immediate weld preparation. quality of a steel pipe comes from the tolerances held at every stage of its production. Steel plate is plasma cut with a precision end bevel on a burn table. Each plate runs through a shot blaster to remove scale. A 4-roll CNC plate bender curls the flat stock into a round pipe section. An automated laser-guided, double-submerged tandem arc welder lays the longitudinal seam to welding standard D1.1. Tabs tack welded to each end ensure full seam coverage. Mid-welds join sections to reach lengths up to 70 feet. Diameters range from 30 to 120 inches, wall thicknesses from 1/4 inch to 1 1/4 inches. 28 inspections verify every pipe before shipment. Some pipe connections have to work underground without any welding at all. At a steel casing pipe facility, sections are produced with precision McKean mechanical joints for microtunneling, pipe jacking, auger boring, and pipe ramming. The pipe is welded in the factory, while press-fit interlocking joints speed installation in the field. Where welded steel pipe reaches its largest diameters, the forming process itself changes. Saw, longitudinal submerged arc welded, pipe is shaped from heavy plate through a multi-stage production sequence. A magnet lifter moves each plate onto the line. An edge milling machine bevels both edges to precise angles. A pre-bender curves the two edges. Then an infeeder pushes the plate into a Jaycees press that stamps the steel progressively into a closed cylinder. A turning transfer car aligns the seam for welding. A tack welder locks the round shape. An inside welding machine runs submerged arc along the internal seam. A backbead cutter removes excess weld material from the outside. An outside welding machine completes the external seam. A 4-way expander rounds and straightens any deformed section. An end-facing machine finishes both pipe ends. A washing device cleans interior and exterior surfaces. An X-ray machine scans every weld for hidden defects. A varnish coating machine applies corrosion protection to the outer surface. Finished pipes are staged for transport. Concrete carries structural load, but it cannot resist the microbial corrosion that eats through sewer pipe from the inside over decades. Adding a protective inner layer changes that equation. One production method uses a concrete HDP composite pipe system that combines structural strength with corrosion resistance. The process begins with the perfect liner, a corrosion-resistant LADRP layer. Automated equipment cuts the liner to the required length based on pipe diameter, with sizes available up to 1.2 meters in internal diameter. The liner edges are then welded together to form a continuous cylinder that will become the pipe's inner surface. This plastic layer provides a permanently watertight barrier and protects the structure from chemical attack. The liner is transferred into the production system, where a thermoplastic molded joint is formed. A maintenance-free shrinking core supports the geometry during manufacturing and helps maintain dimensional accuracy. Reinforcement and structural components are positioned around the liner before concrete placement begins. Self-compacting concrete is poured into the mold and flows around the internal structure without requiring intensive vibration. The concrete shell provides the static strength needed to resist soil pressure, traffic loads, and installation forces, while the Lage pipe liner protects the flow surface inside the pipe. After curing, the pipe moves through automated handling stages. Connection components are assembled, including the perfect connector system used to join individual pipe sections. Each completed pipe then undergoes inspection and tightness testing to verify watertight performance before shipment. The result is a pipe that combines the structural capacity of concrete with the corrosion resistance of DP. Concrete pipe without a liner follows a faster production cycle: vertical casting, immediate demolding, and straight to the curing yard. Wheel loaders feed raw aggregate and sand into storage bins. An automated batching system weighs and mixes the dry mix concrete in a planetary mixer before conveyor belts transfer it to the pipe machine. Steel reinforcement cages are fabricated on a dedicated welding station and placed onto base pallets. The outer mold is positioned and secured. The entire assembly moves vertically under the concrete feeder. A core vibrator compacts the dry mix as it fills the mold, eliminating air pockets. A hydraulic press forms the spigot end at the top. Because the mix is dry enough to hold shape immediately, the outer mold is stripped right after pressing. The freshly cast pipe stands on its pallet. Set rings are placed on top and polythene wrap seals in moisture for curing. A clamp lifts the cured pipe, tilts it horizontal, and a crane moves it to the stockyard. Once the pipe is buried and the system is running, operators need flow data without cutting into the line. A non-invasive ultrasonic flow meter clamps onto the outside of a buried pipe and reads velocity through concrete reinforcement and steel layers without interrupting service. A pipeline network needs access points, and every manhole, cone, and chamber ring is a precision-cast concrete component manufactured before the trench is opened. The Magic 2500 is an automatic vertical dry cast machine for manhole rings and cones up to 2,500 millimeters in diameter. A single operator runs the full cycle. An electric cart delivers base pallets to the forming station. A robotic feeder loads dry mix concrete into the mold. Steel reinforcement and lifting anchors are positioned before forming begins. The machine compresses concrete under controlled vibration to achieve density and dimensional accuracy. After demolding, the finished ring stands on its pallet, walls smooth, edges precise, service connections already cast in. An overhead crane lifts each ring to the stacking area. Products include standard manhole rings, drainage rings with preformed holes, tapered cones, and chamber rings. Each unit arrives at the job site ready to be lowered into the shaft and sealed, with no field forming required. If the surface gives no water, the next answer is depth. The deepest water borehole drilled in Israel reaches whopping 500 meters. Specialized equipment was imported to extract water from that depth. The submersible pump itself is 27 meters long, installed at 960 meters below ground level. One borehole is one source. A country needs a network. The National Water Company operates around 5,100 boreholes, some reaching 5 kilometers into the ground. The new national water carrier connects 5 coastal desalination plants into one centralized system controlling more than 3,000 facilities and 12,000 kilometers of pipeline. where boreholes feed the source, open channels and concrete-lined canals carry the volume. Excavators strip overburden, slope trimmers shape the canal walls, geomembrane is laid, and concrete is poured across the lining to seal the carrier against loss into the surrounding ground. Connecting a borehole to the national system means driving pipe through whatever ground lies between them. A horizontal directional drilling rig sets up on solid rock terrain. Large diameter steel pipe sections are welded into a continuous strings and laid out behind the entry point. A reamer cuts the pilot bore wider while bentonite drilling fluid lubricates the bit and stabilizes the bore wall. The operator inside the control cab tracks torque, rotation speed, and bore pressure on screens, steering the head through stratified rock. As the reamer pulls back, it draws the welded pipe string behind it into the bore. Excavators outside the entry support the pipe string and keep its alignment as it advances into the ground. The coated steel pipe ends up inside the rock without any surface trench cut into the terrain above. A single company has carried the water file at national scale since 1937. It collects surface water, drills shallow and deep groundwater wells, desalinates brackish and seawater, and reclaims wastewater for agriculture. A centralized control system manages 3,000 facilities and 12,000 kilometers of pipeline supplying water to over 9 million residents. Bringing a new source online into a live network is its own engineering problem. When a new desalination plant in the Western Galilee was connected to the regional supply, controlled flow tests ran for weeks. Switching from groundwater to desalinated water can loosen iron oxide from older pipes inside homes, briefly tinting tap water until lines flush clear. 12.00 kilometers of pipeline do not stay in the ground by themselves. Every meter of that network has to be laid, joined, monitored, and someday repaired before the next break stops a city cold. An acoustic fiber optic system detected a failing 54-inch main in a wooded area, where 100,000 residents faced losing water during a heat wave. Crews cleared access within 32 hours and closed 10 valves to isolate the damaged section. The largest valves required more than 400 turns each. After draining the line, a replacement section was installed and the pipeline restored. Following laboratory testing, water service resumed before a major outage could occur. A city water main cannot simply be shut down whenever a new connection is needed. Instead, engineers use a process called hot tapping, allowing a new 225 mm branch line to connect to an active 400 mm main while water continues flowing under pressure. The process begins with surface preparation. The outside of the polyethylene pipe is cleaned and scraped to remove oxidation that could weaken the bond. An electrofusion saddle is prepared the same way, then clamped securely onto the main pipe. Electrofusion cables connect the saddle to a welding unit, which applies a controlled heating cycle to fuse both components together. After welding, the joint is allowed to cool before further work begins. A gate valve assembly is then attached to the saddle. Before drilling, the connection is pressure tested to confirm the weld and flange seal remain leak-free. Once approved, a hot tapping machine is mounted onto the valve. With the valve opened, a hole saw cutter advances through the live pipe wall while the main remains fully pressurized. The removed section of pipe is captured by the drilling system and withdrawn safely through the valve. After drilling is complete, the valve is closed and the equipment removed. The new pipeline branch is now connected without interrupting water service. At national network scale, every joint in a buried pipeline gets seated the same way, one section at a time, lowered into a trench and pushed home into the bell of the section before it. A 54-inch PVC pipe is slung from two straps under an excavator, lowered into the trench, aligned with the bell of the previous section, and pressed home until the depth mark seats flush. Trenches work where there is open ground to dig. But under a city center, beneath active boulevards and the water table itself, the only way forward is down, and the cutter head doing that work has to come back out the same way it went in. Engineers cut and welded reinforcement beams in the wet 12-meter shaft to brace a 1,720 millimeters microtunneling cutter head before lifting could begin. Heavy lift cranes were rigged to the cutter head's anchor points, and the entire cylindrical assembly was hoisted vertically out from beneath the busy boulevard and lowered onto a waiting heavy transport truck. A second lift recovered the submersible pump, caked in groundwater silt. The boulevard stayed open throughout. Next, the segments are ready. The machine that places them has to be assembled, and a tunnel boring machine the diameter of a building cannot be driven to site in one piece. A tunnel boring machine arrives at the launch site as a series of separate heavy components. Trucks deliver each section, and large cranes unload them onto the staging area beside the launch shaft. Engineers reference layout drawings and technical schematics on the surface to assemble major subsystems in the correct sequence. The massive circular cutter head frame is built up section by section with cutting tools mounted into their housings. Surrounding shield structures are joined to the cutter head assembly. Heavy-duty cranes then hoist each assembled section vertically down into the launch shaft. Inside the shaft, the team connects the cutter head to the main drive unit, fits structural rings around the shield body, and threads the screw conveyor that will carry excavated material back through the machine. Crews tighten heavy industrial bolts at every flange. Welders work continuously to fuse load-bearing connections in the confined space below ground. Finally, the trailing gantry, carrying control systems, electronics, ventilation, hydraulics, and the conveyor that moves spoil back out of the tunnel, is lowered and linked behind the main shield. When the last connection is made, the tunnel boring machine is a single continuous machine, ready to advance into the bored face and begin laying the precast segments behind it. Some underground work is planned years in advance. Some begins the moment a main fails under a street. A ruptured 18-inch cast iron water main was isolated using 3-line stoppers. The failed section was cut out with a chainsaw rigged to spray cooling water, and a replacement piece was lowered in and bolted using couplings. Every customer above ground stayed in service throughout. Some lines cannot be shut down for an upgrade. The new pipe has to slide inside the old one while raw sewage still flows through it. A 960 millimeters GRP pipe is lowered into the launch shaft at night and slip line directly beneath an active sewer line. Beneath central Tel Aviv, a 1,720 millimeters GRP sewer line advances by microtunneling with laser-guided alignment and hydraulic jacks pushing pipe segments beneath busy streets. Behind every kilometer of tunnel excavated by a tunnel boring machine are thousands of curved concrete segments, each one cast, cured, and stacked before the machine that lays them ever turns underground. Steel reinforcement cages are welded to shape. Molds are cleaned and sprayed with release agent. Reinforcement is lowered in, the mold is sealed, and concrete is poured under vibration compaction. Heat curing accelerates strength. The segment is demolded by vacuum lift and moved to intermediate storage. A bonding layer and hardboard cushion pads are glued onto the contact faces. A joint sealing strip and gasket frame are seated around the rim. A mechanical press forces the gasket flush into its groove. Automated cranes scan, sort, and stack the finished segments at the outdoor yard until they reach full design strength. Threading pipes beneath city streets is one scale of underground work. Driving a water tunnel for tens of kilometers through a mountain range is a different scale entirely. Israel's first water transmission tunnel, built as part of the fifth system to Jerusalem, was excavated through the complex geology of the Judean mountains. At the front of the tunnel boring machine, a massive rotating cutter head grinds directly into the rock face, breaking hard stone into smaller fragments. Behind the cutter head, crews install precast concrete lining segments that form the permanent tunnel structure. As geological conditions change, engineers adjust operating parameters to keep excavation progressing safely through the mountain. Behind every kilometer of tunnel is a national-scale water plan. The fifth system to Jerusalem cost about 700 million US dollars over 6 years, pumping desalinated seawater from the Mediterranean coast up nearly 900 meters to the city. The Kisalon water tunnel runs 13 kilometers at depths reaching 350 meters beneath the Judean mountains, supported by reservoirs, 2 pumping stations, and a fiber optic monitoring system. The same machines that bore water tunnels also bore the metro lines crossing under cities and watching them break through. One station at a time makes the scale of urban tunneling real. 2 tunnel boring machines advanced through the eastern section of the Red Line in Tel Aviv across nearly 2 years. The first machine broke through into Depot Station in May 2017, then advanced to MEA, Moshavat Station by December 2017. The second machine reached Chamber Station in July 2018. Both machines then converged on Ben Gurion Station beneath the water table, one breaking through in mid-January 2019, the second following 10 days later. Each breakthrough required the cutter head to emerge precisely into the pre-built station box, on alignment, on grade, with the surrounding city carrying on above without disruption. Before a microtunneling machine can launch, the bottom of its shaft has to be sealed against the groundwater pressing in from below. A 1,720 millimeters launch shaft floor is cast in 12 meters of standing groundwater near the Tel Aviv coastline. Divers work beneath the surface while concrete is pumped down through trimmy lines. Sealing the bottom of a 16-meter deep shaft under 12 meters of standing water cannot be done from the surface alone. A diver descends in a steel cage with a fully sealed helmet, a comms linked to the surface, and air supplied through an umbilical, then guides the tremmy pipe to place concrete across the shaft floor. Every kilometer of pressurized pipe under a city needs an access route to the surface, and that route is built from precast concrete modules lowered into the shaft one box at a time, with stair sections threaded between them as the shaft rises. Installing a deep access shaft over a live pressure main in the middle of a busy intersection means working at night and finishing the surface by morning. A 9-meter deep stair manhole was set over a 1,720 millimeter sewer pressure line under 10 meters of groundwater. A heavy crane lowered the precast concrete boxes one at a time from a flatbed trailer, guided into position by crew on the ground using radios and hand signals. Stair sections were threaded into the shaft as it grew. Sealant was applied along every joint to keep groundwater out. By daylight, a wheel loader was backfilling around the structure. Paving stones were being relayed for the sidewalk, and a paver and roller restored the asphalt before the morning rush. Pipelines and tunnels move water across a country. Desalination creates that water in the first place. The answer Israel arrived at was the sea. A desalination plant begins with massive concrete foundations, intake structures, and processing infrastructure built long before membranes arrive. Reinforced concrete steel frameworks and precision construction prepare the site for a facility designed to produce 158 megaliters of fresh water per day. Turning seawater into drinking water depends on one piece of equipment more than any other: the pump that pushes it through a membrane at extreme pressure. At the heart of every SWRO plant sits the high-pressure membrane feed pump, the unit that forces seawater through the reverse osmosis membranes at the pressure needed to separate salt from water. Pump designs built for this duty reach flow rates up to 7,000 cubic meters per hour in single-stage, double suction configurations with operating efficiencies above 90%, and a related end suction range extends to 9,500 cubic meters per hour. Beyond the main feed pumps, auxiliary systems handle second-pass filtration, booster stages, backwash cycles, and energy recovery devices that capture pressure from the reject brine before it leaves the system, lowering the energy needed per cubic meter of fresh water produced. Before any pump reaches that pressure rating, it has to survive its own production line. The production sequence for a high-pressure pump begins with project review and risk assessment, where engineering requirements and delivery timelines are mapped before any metal is cut. Each pump is then modeled in 3D CAD and run through virtual simulation to verify hydraulic performance, and structural behavior before manufacturing starts. Castings move through the foundry, where metal is poured into shape and passed through heat treatment to achieve the required mechanical properties. Material quality controls and microscopic analysis verify structural integrity before any casting proceeds to machining. CNC machining centers and automated milling then shape the internal flow passages, casings, and impellers to the tolerances the application demands. Final assembly combines manual fitting with heavy lifting equipment to bring large fluid handling components together, and every finished unit runs through safety verification and pressure testing before it is cleared to leave the facility. The standard pumps for desalination must meet. The valves controlling flow through that pressurized pipework are built and proven to standards that do not change with the industry they serve. At a hydropower station, four butterfly valves rated DN 2000, 2 meters in diameter, were manufactured to replace turbine inlet valves that had never been changed since the plant opened decades earlier. Before any valve left the factory, each one went through a body pressure test at 20 bar, followed by a seal test at around 17.6 to 18 bars, with zero leakage recorded across all four units. Function testing followed the same sequence for each valve: pressure test, then operational cycling of the closing mechanism, witnessed and signed off before the unit was cleared. The design brief required the new valves to match or exceed the flow capacity of the originals, improving the overall efficiency of the plant they served. Once testing was complete, attention shifted to transport. Moving valves of this size to a remote site required route planning for narrow roads, police escorts, and temporary closures along the final approach. The project's stated goals were safety, schedule, and budget, and all four valves passed pressure and function testing before departure. The same sequence, casting and machining to specification, pressure testing of the body and seal, function testing of the operating mechanism, and route planned heavy transport to site, applies to the high-pressure valves and PEEP work used throughout a seawater reverse osmosis plant, even though the application here is hydropower rather than desalination. Put the pumps, the membranes, and the valves together, and this is what the finished process looks like. The Kayaphidian plant draws seawater through submerged intake piping, screening out debris before pumping it to the main process. Pretreatment removes suspended solids and filters particles down to around 20 nanometers before a cartridge filter protects the membranes. 5 reverse osmosis trains, Endeavor, each with 924 elements, across 132 pressure vessels, operate above 55 bars, producing 10,000 cubic meters daily per train with energy recovery cutting power use. None of this works if the membranes inside those pressure vessels cannot be replaced quickly. The barrel system loads spiral wound membranes through manhole access points on either side of a pressure unit rated at 5,000 cubic meters per day. Technicians in protective gear slide old elements out and new ones into position by hand, with no specialized tooling required for exchange. Replacing a membrane element is not a simple swap. It follows a fixed sequence every time. Loading membrane elements into a pressure vessel follows a fixed order. The permeate pipe manifold is disconnected first. Then retaining rings and end caps are removed from both ends of the vessel using an extractor. The inside of the vessel is flushed and lubricated before the brine side end cap and thrust cone are reinstalled. Elements are then loaded one at a time from the feed side, each connected to the next with a lubricated interconnector, taking care not to overload the connector with the next element's weight. Once all elements are in place, a feed spacer holds the final element, and the feed side end cap is closed and secured with its retaining ring. Where surface water is the source, an automated plant runs every step. Water from rivers and a 15.5 billion gallon reservoir is pre-treated, sent through an active flow clarification process using sand and polymer, disinfected with ozone, then polished through biofilters and granular activated carbon, up to 120 million gallons of finished drinking water per day. Before wastewater treatment begins, inlet screens remove rags and debris that could damage downstream equipment. These screens operate continuously and collect large volumes of material each year. When a chain roller wears out, a split replacement roller can be installed directly on the chain without removing the screen. The old part is cut away, the new roller is clamped and secured, and the screen quickly returns to service. A full treatment train means handling every stage in sequence. Screening removes large debris and grit. A moving bed biofilm reactor handles secondary biological treatment. A clarifier separates solids. Ultrafiltration polishes the effluent for non-potable reuse. Recovering water means turning wastewater into a usable resource. The process relies on biology as much as engineering. Raw wastewater enters a receival lagoon before moving into a nitrifying reactor, where aeration helps convert ammonia into nitrate. The flow then enters an anoxic tank, where microorganisms remove oxygen from nitrate and release nitrogen gas. After settling in a sequencing batch reactor, the treated water passes through sand filters before meeting discharge standards. At the heart of desalination and high-grade water reuse sits one component, a thin film component membrane wound into a spiral cartridge. Feed water flows tangentially across the membrane surface under pressure. Filtrate passes through, and concentrate accumulates at the opposite end. Reused water and new water both end at the same checkpoint. The polishing stage that confirms it is safe to drink. Settled water flows by gravity through anthracite coal and sand filters. Online turbidity meters check clarity continuously. Ultraviolet reactors with medium pressure lamps damage the genetic material of protozoa, finishing disinfection. Producing water from the sea is one half of the answer. Using every drop, that water once it reaches a field, is the other half, and Israeli precision irrigation begins long before water hits the soil at the filter. Before irrigation begins, screen filters are serviced and cleaned. Coarse and fine screens are removed, washed and inspected, while bearings, gaskets, shafts, and seals are checked for wear. After reassembly, control settings are verified and the system is pressurized. Several manual backflush cycles confirm proper operation. Maintaining clean filtration ensures irrigation systems deliver water reliably while reducing waste across fields where every drop matters. Israeli drip irrigation technology runs farms across the globe. A subsurface install on a rotational corn and bean field uses a pressure-compensating drip line, a design that emits the same flow regardless of elevation change across a field. The zero point 0.1 gallon per hour emitter is chosen for economics in this case. It lets the system run on 8 zones instead of 16, cutting installation cost. Pallets of prepackaged tape arrive on site and are loaded onto reels for a plow with 7 shanks. 3 operators ride the plow, each watching reels to confirm clean spooling. GPS on the tractor keeps every line straight in its rip path. A trencher follows behind to cut the sub-main holes. Holes are drilled in the pipe, gooseneck risers tie into each tape line, and the trench is backfilled. A concrete pad pours over the well. The filter pad receives a sand media filter, a screen filter as backup layer, an injection pump for fertilizer or crop protection chemicals, and a valve bank control unit. Getting water to the field is its own challenge. Canal lining keeps every cubic meter moving without seeping into the ground. A paver lining machine pushes ready-mix concrete up a steel mesh reinforced slope, leaving a finished concrete surface. Every technology covered so far, desalination, recycling, microtunnels, drip lines, only works when one institution coordinates them. The Water Authority runs 5 desalination plants: Hadera, Sorek, Pamakim Ashdod O, Sorek, Pamakim Ashdod Ashkelon, targets 90% of drinking water from desalination and ties it into a national grid. A drop tracks the entire system. Mediterranean seawater enters a desalination facility, reaches a home for drinking and washing, gets sent to a recycling plant and finishes its life irrigating crops through a drip line. Today, desalination supplies much of Israel's drinking water nationwide. But desalination is only one part of the system. Precision irrigation, wastewater recycling, river restoration, and technologies that harvest water from the atmosphere help stretch every available drop further across farms, cities, and industries. Building a national water network is rarely as simple as laying pipe from one point to another. Routes must cross highways, railways, rivers, and developed areas while keeping water flowing reliably. Tunnels, crossings, and buried transmission lines become part of the system itself. The farther water must travel, the more engineering is required to move it safely to the people who depend on it. Behind every desalination plant is a network of pressure vessels, filters, pumps, and membrane housings working around the clock. Water production does not depend on a single machine. It depends on thousands of engineered components built to contain pressure, resist corrosion, and keep fresh water moving through the system every day. Water can only travel across a country if the network beneath it lasts for generations. Israel's water empire also depends on pipelines built to survive decades underground. Corrosion, leakage, abrasion, and ground loads can destroy a poorly designed system long before its planned lifespan ends. That is why modern water infrastructure combines multiple layers of protection. Concrete provides strength against external loads. Internal liners protect against corrosion and chemical attack. Watertight joints reduce losses across long transmission routes. Reinforcement structures distribute stress while allowing the pipeline to withstand changing ground conditions over time. Many of these systems are designed for service lives measured in decades rather than years. Once buried, they become invisible parts of a national network that most people never see. Yet every reservoir, pumping station, treatment facility, and city connection depends on them. Without durable underground arteries, even the largest desalination plant would have no reliable way to deliver water where it is needed. Other arid nations follow the same national scale playbook, designed around decades of demand. A 2018 water security strategy projected demand out to 2036, leading to a first-phase desalination plant of 150 million gallons combined capacity feeding a vast pipeline network. Distribution flows from a coastal plant through a main distribution center to the northern Emirates, with transmission lines crossing the entire central region with coordinated construction phasing. Behind any national water system sits decades of pipe manufacturing, engineered transmission pipe, precast structures, and trenchless components, products that convey, treat, store, and manage water for whole urban populations. They form the backbone of cities, sustained quietly by daily industrial output. There are jobs out there most of us will never do, run by machines we may never touch. Subscribe for more behind-the-scenes engineering. Thanks for watching. We'll see you in the next one.